Good afternoon. I am Heather Kaylor, the NASA Technical Fellow for Flight Mechanics at the NASA Engineering and Safety Center. Today we are presenting the first of 3 webinars on new sizing frameworks for electrical vertical takeoff and landing urban air mobility aircraft. This webinar is being recorded for distribution on the NASA Academy website. I will moderate a question and answer session at the end of the talk. Please queue up your questions in the chat feature or use the raise hand icon to ask your questions. Dr. Iman Shakouri is the director of Auburn University's Vehicle Systems Dynamics and Design Laboratory. His research areas include the sizing and simulation for unconventional aircraft concepts, including electrical vertical takeoff and landing, eVTOL, urban air mobility aircraft, with all-electric and/or hybrid electric propulsion system architectures. Dr. Chakraborty is striving to create a workflow or pipeline that starts from vehicle sizing and configuration trade studies, proceeds to stability and control analysis, followed by control law development, piloted flight simulations and flight simulators, and then ultimately flight tests of subscale demonstrators. Let's welcome Dr. Chakraborty.
Thank you very much, Heather, and good morning, good afternoon to everybody that's tuned in. Thanks to NASA for giving me this opportunity to present some research being done at my lab. So the title of today's talk is Sizing and Optimization of a Lift plus Cruise Urban Air Mobility Concept with Electrified Propulsion. So just a little bit about me. From 2018 to the present day, I've been an assistant professor at Auburn's Aerospace Engineering Department. And prior to that, I was a research engineer at Georgia Tech, which is where I did my PhD and master's in aerospace engineering. I did my bachelor's in mechanical engineering from NIT Trichy in India. I'm fairly involved with the AIAA, and I'm also very enthusiastic about aviation. And I'm a private pilot, and I really enjoy flying. And I find that it influences the research in my lab in many ways. The lab is the Vehicle Systems Dynamics and Design Lab, or VSDDL, and as the name suggests, our work focuses on vehicles, so flight vehicles, both conventional and unconventional. We focus on their systems, so propulsion systems, other secondary systems, sizing and analyzing those systems. Then dynamics, so we're involved in flight simulation, stability and control analyses, control law development, and then finally, we try to capture the effects or the impacts of all of these on the overall design of the flight vehicle or the aircraft. So our work has been funded by NASA, by the FAA, and also by the U.S. Air Force Agility Prime program, either directly or through collaborative projects with our many industry collaborators, some of whom are shown on this next to the pie chart over here. In particular, we make a lot of use of the PEACE framework for aircraft sizing, which we're going to go into detail in this webcast. We also developed and used the MADCASP stability and control and flight simulation capability, which we developed with funding from NASA Langley. And that's going to be the prime topic of the second webcast. And finally, we developed flight simulators in our lab, which we use for piloted simulation studies. And we're going to deal with those in the third webcast. So what motivates research at the VSDDL is basically a number of emerging challenges associated with new flight vehicles that are under development or undergoing testing. As most of you are definitely aware of, there are a lot of sizing and performance analysis challenges associated with these types of flight vehicles. And a lot of that stems from their unconventional configurations. We simply don't have enough historical experience with those types of configurations, and that increases the uncertainty. They have got electrified propulsion systems, either they're fully electric or they're hybrid or turboelectric. So electrification of the propulsion system architecture, distributed propulsion, and a lot more aeropropulsive coupling. So these are some of the challenges that we have. There are also other stability and control challenges. So these are over-actuated systems. So if you look at all of the pictures on the right and many other vehicles like these, they all have more control degrees of freedom than motion degrees of freedom. which means there's no one unique way to control these in flight. We don't know about their dynamic stability characteristics. We don't know as much because obviously they're unconventional configurations. We have to think about how to design the flight control system for these aircraft to enable what's called simplified vehicle operations, or SVO, which is to permit pilots to proficiently and safely operate these with far more streamlined, less time-consuming, and less expensive training requirements. And also the evolving role of the human pilot or operator. So obviously these will be more and more automated, but what is the pathway that that automation follows? So all of these influence our research at the VSDDL. We try to work along this research and development pipeline, whose first step is basically vehicle sizing, performance analysis, and optimization. So that's basically the topic of today's webcast. And after we've done that, we focus on stability and control and flight control system architecture design and optimization. And we'll get into that in next week's webcast. And once we've done that, we like to deploy our simulation models to our flight simulators and then do piloted simulations to test this simplified vehicle operations, or SVO, concept. And that's going to be the topic of the third webcast. And finally, and we're just getting into this now, we don't have much experience, subscale prototype flight testing. So there'll be a lot more of that at VSDDL in the years to come. The content of the webcasts are being drawn from 3 papers that we presented at the recently concluded AIAA SciTech conference. So you have the links to these papers over here. I understand that a PDF version of this presentation is going to be made available, and the hyperlink should still work. Okay, so to get started with the performance analysis for flight vehicles, a fundamental consideration is are some energy concepts. So what does that mean? So if you think of the aircraft as a container of energy, which could be either kinetic energy through speed and potential energy through altitude or height, well, then the propulsion system is what is adding energy to that system. And then drag is what is dissipating energy out of that system. So if you were to write an energy balance relationship based on these principles, that would end up looking like this. So what this is basically saying is that the rate at which the propulsion system pumps energy into the system, less the rate at which drag dissipates energy from the system, must, by energy conservation, be equal to the time derivative of the potential and kinetic energies of the flight vehicle. And typically, we then make the assumption that thrust generated by the propulsion system is basically aligned with the direction of motion, and drag by definition is opposite to the direction of motion. And so this relationship simplifies to this more familiar relationship that we use quite a lot in aircraft performance analysis. So basically, thrust power minus drag power divided by weight is specific excess power, which is the rate at which the energy height of the aircraft, which is height plus an equivalent height from kinetic energy, changes. And all of that is fine, provided the assumptions that went into it are valid. So for instance, the assumption that thrust is aligned with velocity is a good assumption for conventional fixed-wing aircraft at reasonably high velocities, but becomes less of a valid assumption at low velocities where the aircraft is flying at a higher angle of attack. It is not at all accurate in those scenarios, and it's not valid when a significant thrust component is orthogonal to the flight path. So think of the flight of a helicopter, where there's a significant component of thrust almost orthogonal to the flight path of the vehicle. And so that is not going to be, this relationship is not going to be valid then. And now consider what's going to happen in hovering flight. So both sides of this equation collapse to zero because the velocity is zero in a pure hover. So the equation is still valid, but not particularly useful if we're trying to use it to assess hovering power requirements. So further, this equation is treating the aircraft as a point mass. So it is not really explicitly considering the fact that the aircraft needs to have rotational equilibria as well. So in other words, it needs to be in trimmed flight. So that's not being considered. And as we'll see later on in today's talk, trimming requirements, so the power required to trim the aircraft and about the roll, pitch, and yaw axes, is going to have a significant impact on the sizing of the propulsion system. That's not being considered over here. So what are the takeaways? Well, we have to consider force and moment equilibria in addition to the power balance shown over here. And we have to somehow generalize these energy concepts to be applicable to vehicles that use wing-borne lift, rotor-borne lift, and also buoyant lift, and also combinations thereof. So in other words, we want it to be generally applicable to atmospheric flight vehicles. So that was our motivation when we started to develop what we now call the PEACE framework. So we started by removing any particular appearance or form of the flight vehicle. So as you can see, it's represented here by an egg-like shape, and that's very deliberate because we want to think in terms of a generic blob or flight vehicle which is flying through the air. What do we know about it? Well, we assume that we have some way of defining some kind of a long axis, a longitudinal axis on this vehicle, so that with reference to that, we can define an angle of attack and a flight path angle. So that's fair. This vehicle could have buoyant forces on it. So that's that FB that you see over here. Buoyancy is a factor. Obviously, we know there's weight. And we assume that there are aeropropulsive forces. Okay, now notice that we're saying aeropropulsive forces on the vehicle along the direction of motion orthogonal to it, and also a net pitching moment on the vehicle. Okay. So now, if you write the translational equations of motion in the wind axes for this vehicle, then this is what that would look like. So we're taking into account that these equations are written in a non-inertial frame of reference, and that's why you find this coupling term over here, angular velocity coupled with speed. If we now break that into scalar equations along the x-axis and the z-axis and separate out the gravity forces. The gravity forces are easy because we know they always act down. So we end up getting two equations of motion, two scalar equations of motion, where we now have the net air reactions on the aircraft. And the net air reaction means the net push of the air on this aircraft, whatever might be the cause of said push. So we're trying to keep things very general over here. And then following that, you do a little bit of algebraic manipulation. And then you can establish that the rate of change of energy height is actually the air reaction in the direction of motion times V divided by W. And the difference between this and the previous relationship is, notice that we have not broken out these net air reactions into thrust and drag. We've called it aeropropulsive reactions. And this is going to become important for vehicles where it's not a trivial task to separate aerodynamics and propulsion. So if there's a lot of aeropropulsive interaction, the lines between what is thrust and what is drag becomes somewhat blurry. And so what we're trying to enable over here is the ability to do the analysis without having to strictly differentiate this is thrust and this is drag. So they're all aeropropulsive forces as far as the PEACE framework is concerned. Okay, so we've implemented the PEACE framework such that the functional form of what we call the aeropropulsive performance model is invariant to vehicle configuration and propulsion system architecture. So whether it's a fixed wing fuel burning general aviation aircraft or a hybrid electric VTOL, the functional form of the APPM will remain unchanged. And this is what that functional form looks like. So on the input side, we need to be able to specify what the angle of attack and flight path angle are. Okay, so we can define the trajectory of the vehicle. We need to know what the status of the vehicle's control effectors are because, like I mentioned before, we're explicitly considering vehicle trim. And then the outputs include the aeropropulsive reactions on the aircraft and also the moments on the aircraft, which we use to calculate force and moment residuals about the various axes in order to test whether the aircraft is in a state of trim and also to enforce the constraint that the aircraft has to be in a state of trim. Other outputs are the rates of change of energy source masses. So for instance, if you're burning fuel, what is the rate at which fuel is being depleted? So that is the rate at which the mass of the aircraft is reducing. If it's an electrified propulsion system, then there is no rate of change of mass. But whatever the type of propulsion system, whatever the energy source, there will always be a rate of depletion of energy. and that's being captured by these DE/dt terms over here. So we're looking at the rate of change of energy mass and the rate of change of energy content of the energy sources. Now that APPM is solved inside what we call the flight mechanics model. And the flight mechanics model, or the FMM, can be solved in a couple of different modes. So for instance, we can solve it in power mode, where we're trying to answer the question, okay, I've defined a flight condition. I'm going at a certain speed, at a certain rate of climb or certain altitude. How much power do I need to sustain this flight condition? Okay, and that's basically solving the APPM in power mode. Flight math mode is basically saying, I'm setting a certain power level. Tell me what flight path would result as from this. And then in acceleration mode, I'm setting a certain power level. Tell me what acceleration would result from that power setting. And then finally, trim mode, which we're going to make use of a lot in today's talk, which is considering also rotational equilibria, all three axes, in addition to force equilibria. And that's to basically determine whether the aircraft is in a state of trim. All right, so all of that now gets put into the PEACE framework, and PEACE stands for Parametric Energy-Based Aircraft Configuration Evaluator. Okay, so this flowchart over here is a graphical depiction of how the analysis workflow goes within PEACE. So let me walk everyone through this. As part of the setup, we need to specify the aeropropulsive performance model, right, for the aircraft. Weight equations or weight estimation relationships will allow us to determine the weights of the various components of the aircraft. A definition of its geometry, so what are the wings connected to, where are they connected to the fuselage, what else is connected to the fuselage, and so on. And then a set of update rules for this geometry. So as the aircraft sizes through multiple iterations, these rules determine how the geometry is being scaled up or scaled down while that's happening. We also have to input technology states of the art. So the states of the art of components such as motors and batteries and so on. A set of performance constraints that we absolutely need the vehicle to be able to satisfy and achieve. Payload and range requirements, a mission profile. And finally, once it completes its design mission, we don't want it to return with zero energy. We have to specify what the end of mission energy constraints are. So return from the mission with no less than certain energy reserves. And then finally, we start with a guess of maximum takeoff mass. With that guess of maximum takeoff mass, first we compute the geometry of the aircraft. And so within PEACE, we have a geometry model. Following that, we run the power sizer, which is now going to find out how much power is required to satisfy each and every one of those point performance constraints. And so basically, it's sizing the propulsion system components. This is going to be followed by evaluation of the empty mass of all the different components of the aircraft, and then subtracting out the empty mass and the payload from the guessed maximum takeoff mass. We're going to get an understanding of how much energy mass we've got on board. And that will then trigger the actual analysis of the mission profile. So segment by segment, this mission profile is going to be evaluated in order to find how much energy remains at the end of the mission, if that's the amount of energy you started off with. And then that is then compared to the end of mission energy constraints. And then this converger will vary the maximum takeoff mass up or down in order to converge on the energy required to perform the mission. So that, in a nutshell, is the workflow within PEACE. And we've used PEACE for a couple of different papers already. One of the first papers we did was to demonstrate that we could use PEACE to evaluate three very dissimilar flight vehicles. So a fixed-wing GA aircraft that burned fuel, an all-electric eVTOL, and a hybrid lift airship. So that was to demonstrate that the underlying methodology was generalized. Since then, we've also analyzed lift plus cruise aircraft that you see over here, a tilt-wing aircraft that you see in the middle. So each of these red nacelles not shown over here is a propulsor or propeller attached to them. And then more recently, the lift plus cruise configuration that we're going to talk about in today's webcast. Okay. So lift plus cruise. A lift plus cruise means that there are separate propulsors for vertical thrust or lift, and then forward thrust for cruise. So the advantage of this configuration is that aerodynamically, it's simpler than vectored thrust concepts. And by vectored thrust, I mean tilt wing or tilt rotor configurations. The aerodynamics of the liftless screws are a lot simpler than those. But the disadvantage is once you get to forward flight or cruising flight, those lift propulsors are basically deactivated, which means that they're dead weight and they're adding drag. So there's an advantage, there's also a disadvantage. Now, this particular configuration that you see over here, like any other liftless cruise configuration in vertical flight mode, so that means hover and low speed flight, it's using the differential thrust of lift propulsors for attitude control about roll, pitch, and yaw axes, simply because the conventional control surfaces are ineffective because there's no airflow over them. And in forward flight mode, obviously the lift propulsors are deactivated, the conventional control surfaces are being used for roll, pitch, and yaw control. And then as the aircraft speeds up from vertical flight mode to forward flight mode, there has to be control allocation and blending to basically blend out the use of the lift propulsors and blend in the use of the control surfaces. So this table below shows a lot of different control effectors that this vehicle has that are available to affect control. So it's clearly an overactuated system. Now, if we cannot trim, we cannot fly, which means that control allocation and trim considerations under both nominal and off-nominal flight conditions are part of the sizing approach in peace. And we're going to see later how big of an impact this can have on the sizing of the propulsion system for a VTOL aircraft. Now, a little bit about how we're analyzing this. So this, what you see over here, is a wireframe depiction of the aircraft configuration within Peace. So Peace is implemented in MATLAB. So this is a MATLAB generated graphic. All the lifting surfaces are discretized into strips, and we use a strip theory-based approach for analyzing the aerodynamic loads on lifting surfaces. So the sectional aerodynamic characteristics of each of these strips, as well as downwash over the lifting surfaces, we get those using FlightStream, which is a vorticity-based flow solver developed by Research in Flight. Research in Flight is a company that has had its origins at Auburn University, so we work very closely with them, and we've worked out a way to take aeropropulsive characteristics identified using FlightStream and then incorporate them within the APPM that exists within Peace. For non-lifting surfaces or non-strip components like fuselages and pylons and nacelles and things that make more drag and not as much lift, we analyze those separately in the form of lookup tables. So it's very much a build-up approach towards aerodynamics. All the propulsors are modeled using a blade element momentum theory model, which is coupled with a Pitt-Peters dynamic inflow model. So that lets us evaluate what the forces and moments at each of these propulsors would be. To calculate mass properties, we use component weight equations for GA aircraft, and we also calculate explicitly the weights of propulsion system components such as motors and batteries. In addition to calculating the masses, we know where these masses are located because, as you can see, we have a geometry model, and that lets us calculate where the center of gravity of the aircraft is, and also lets us calculate the inertias about the roll, pitch, and yaw axes, which are also going to be important later on. The geometry update rules, as I mentioned, this is a set of rules that defines how should the geometry update as a vehicle is scaling up or down. So as an example, if while the aircraft is sizing, the diameter of one of these lift props increased, as you can see, if no other action was taken, they might interfere with another lift prop or with the fuselage. So these geometry update rules have to specify deconfliction rules as well. Well, what else are we going to move to resolve that kind of a geometry conflict while the aircraft is resizing? We're very particular about geometry within Peace, so that wireframe model that's generated in MATLAB can be exported in AC3D file format. So that's this center picture over here. And then from AC3D, we can import that into FlightStream, which I mentioned is the flow solver that we use. And we can get aerodynamics, aero numbers from FlightStream. We can also export it into X-Plane, which is what we use for our flight simulators. And that's how, after we've sized the aircraft, we deploy it to the flight simulator. So geometry is a pretty central component of all our activities. All right, so if you recall, I said electrified propulsion system architectures. I did not say electric. So there are different types of electrified propulsion architectures that we're interested in considering. And the first one is an all-electric architecture where all the propulsive power required by this aircraft is being supplied from battery packs. So what's happening over here? We have n number of battery packs that are supplying energy to all of these 8 lift props and also the cruise prop. So that's the propulsion system architecture. And if you were to write energy balance relationships across each of these components, basically saying that energy power out equals power in times efficiency, and then you resolve nodes like this where a certain amount of power is coming in, and that must equal all of this power going out. If you write out each of those scalar equations and then you capture them in matrix form, you end up with this power flow system or system of power flow equations, where you have a square matrix and then a vector of component powers that we want to solve for, and then a vector of boundary conditions represented by the power consumed by each of these propulsors that we already know from solution of the APPM. So if we were to invert this system, which we'll be able to do if it's square and non-singular, we'll be able to find the power flowing through each of these components. And we're going to use that when we fly the mission, and we're going to use that when we size each and every one of these propulsion system components. So that's the all-electric, believe it or not, the easiest one to analyze. Now let's consider a turboelectric architecture, or TE, where those same propulsors now are being powered by power generated from a turboshaft engine or engines that drives gearbox, and that's then connected to a generator which makes electrical power. Okay, so even though the motors are consuming electrical power, the original source of that energy is actually the energy within fuel that this turboshaft engine is consuming. So in a very similar manner, if you were to write all the power flow relationships across all of these components, do your beam counting, and then put them in matrix form, you end up getting the power flow equations for the turboelectric architecture, which again, this can be inverted, and we can solve to find the power through pulsing through each and every one of these components. That's also relatively straightforward. Where things get complicated is if you go hybrid. So here's a hybrid electric architecture, and it's not the only possible hybrid electric architecture, but it's one possible hybrid electric architecture where this turbo generator power path and the battery power path are basically sitting in parallel with one another, and they can both push power to the lift propulsors and the cruise propulsor. So now, and on top of that, the turbo generator power path can supply recharging power to recharge the batteries in flight. So that's another possibility. So once again, if you write out all these power flow equations and you capture them in matrix form, and you do your beam counting, you're going to find that you're 2 equations short. It is not a square system as it stands because, well, there's more than one way to run this propulsion system architecture. There are an infinite number of combinations of power coming from the battery path and the turbo generator path that can add up to the required power. And further, we don't know how much power is going in the recharge channel and how much power is going in the supply channel. So there are multiple sources of non-uniqueness in this system that make it non-square. So to square up that system and make it invertible, we have to add as many closure relationships as the number of non-uniqueness in our system. And in this case, we have to add 2 closure relationships. And those closure relationships are a mathematical way of indicating what is the operating mode of this hybrid electric propulsion system architecture. So for instance, suppose there's a nominal mode in cruise in forward flight where the lift props are off and whatever power the cruise prop takes is being supplied from the turbo generator power path. Okay, and the batteries are not contributing anything. So you could specify that mathematically by setting appropriate values to these alpha, beta, gamma, delta, and B parameters in these closure relationships. Another mode would be a recharge mode, right, where all the power required for flight is being provided by the turbo generator power path, and it's also providing recharge power to recharge the batteries. So this is a mathematical way of specifying how much recharge power is being supplied and the fact that the battery is being recharged and not supplying power. And then finally, another mode that we use is offset mode. So offset mode, when there's very high power requirement in vertical flight mode, we assume that the turbo generators are operating and supplying all available power that they can supply, and then the batteries are providing whatever the balance of power is, and there's no recharging going on. So these descriptions of these qualitative descriptions of how the propulsion system is operating, what mode it's operating in, have to be captured through these power flow relationships. And once that is done, once the closure relationships are defined, the system can be inverted and then solved. Okay, so now power sizing. If you look at all these point performance constraints, these are basically evaluated at specific points, and the aircraft needs to be able to hit each and every one of these constraints. Notice that several of them are off-nominal or post-failure constraints, which means that something has failed on the aircraft. A lift propulsor has stopped, or a battery has failed. And in that situation, when you're high and hot, so you're hovering high and hot, you have to be able to hover or still have enough power to maneuver. So it's very important to set these off-nominal or failure flight conditions for the following reason. Let's see how Peace goes about sizing the propulsion system. So these are the constraints that we specified. Peace trims the aircraft at each of these flight conditions. And over here, you see how much power is required by each of those lift props and the cruise prop. And you see that there's a particular failure scenario which sizes the lift propulsor power rating. It is not any nominal scenario, but it's a failure scenario where something has failed that directly sized power. The cruise motor would probably get sized by a climb requirement, and then the battery pack, the power output of the battery packs would get sized by a scenario where one or more battery packs failed. So the takeaways are, we have to consider off-nominal or failure scenarios within sizing because they're directly affecting the power sizing of electrical components. And finally, the only way we can do this is if we actually trim the vehicle while sizing it. Otherwise, we would miss each of these constraining scenarios. Now, when we then evaluate the vehicle over the course of a mission, and so here you see a typical UAM out and back mission, which is 2 missions flown back to back. And at the end of the second mission, you have end of mission energy constraints, which are specified in terms of how much reserve and how much energy has to remain in the battery. So a minimum state of charge that the battery must always have, and a minimum amount of fuel if fuel is being used. So the mission analyzer within Peace will keep checking whether these end of mission energy constraints are being satisfied and adjust the maximum takeoff mass accordingly. When we're doing weight estimation for electrical system components, we do that based on technological state-of-the-art assumptions. So you see this table tabulates various specific powers and power to mass ratios for different components that are used to develop what their weight would be once we've determined what their power outputs are. All right, so now let's do some sizing trade studies. So let's vary wing loading, which is basically the vehicle weight divided by wing area, and then disc loading, which is vehicle weight divided by the total lift propulsor rotor disc area. Let's vary those, and let's vary cruise speed between 175 knots and 225 knots and see how this aircraft sizes. And as you can see very, very quickly, as you go faster and faster, there's an increase in propulsive power requirement, which upsizes the vehicle. It ends up being a heavier vehicle if you want to go faster. And if you look at disc loading, you'll see that there's a bucket or a sweet spot. So particular disc loading, which is a fine balance between efficiency of hover versus the size, weight, and drag penalties of the rotors. And if you look at wing loading, you'll see that there's also a sweet spot of wing loading beyond which there's diminishing returns if you increase the wing loading any further. All right, so next, now that we've established those kinds of trends, let's size these vehicles, all electric, hybrid electric, and turbo electric architectures over a range of single trip distances. So single trip distance means the distance covered in each of these out and back trips. So if we vary that, obviously we're increasing the amount of propulsive energy that has to be on board the vehicle. And let's see how the AE, HE, and TE architecture size up. So if you look at the AE architecture, you see there's a very severe sensitivity to trip distance. So as we start asking for more and more kilometers or miles of range, the weight of the all-electric architecture grows very, very quickly. And that's because of the current state-of-the-art of batteries. If you look at the hybrid electric architecture, so these HE lines over here, you will see that it is not as much of a sensitivity. Why? Because in cruising flight, the energy requirements are being met by the turbo generator power path, which is burning fuel, which of course has a significantly higher energy density than batteries do. And so there's accordingly a significantly reduced sensitivity to to increasing trip distance. And the gray line over here is the turboelectric architecture, which of course doesn't use batteries for its propulsive power requirements, and therefore its performance is unaffected by the assumed technological state-of-the-art of batteries. So over here, we've assumed between 300 and 400 watt-hours per kilogram battery-specific energy at the pack level. All right, so that gives us a quick understanding of how this scenario is going to play out, what architecture, what propulsion system architecture might be in our best interest to consider for a given range and for a given technology level. So as you can see from this chart, there are certain ranges and certain technology levels at which each of these three architectures makes sense. So one of the goals of PEACE was to be able to determine these types of design sweet spots. Now let's look at what happens if we were to size an AE, an HE, and a TE to the same gross weight. Okay, so in this case, that's 2,800 kilograms, which is about 6,000 pounds maximum takeoff mass. And now let's look at what that weight comprises of. So if you look at these columns over here, these pillars, all of them have roughly similar structures and systems weight. However, as you go from all electric to hybrid electric to turbo electric, the propulsion system group weight, which is the weight of all components within the propulsion system architecture, starts climbing a lot. We're including turbo generators, gearboxes, generators, and so on. But at the same time, the battery weight reduces because now batteries are being sized not necessarily to provide all the energy requirements, but to provide peak power requirements. So they end up getting sized by power and not by energy. So as you can see, the battery mass fraction is reducing and it's completely gone for the turboelectric architecture. All right, so now we have an understanding of what the weight composition of these aircraft would be. So now let's try to do some optimization. So now if we were to wrap the PEACE framework within an optimizer and give that optimizer access to certain design variables. And we know in our case, some of the design variables, as you see listed in this table, are continuous variables, wing loading, disk loading, wing aspect ratio, taper ratio, and so on. However, we also have propulsion system architecture, which for us can be all electric, hybrid, or turbo electric. That's a discrete flag. The number of battery packs in the propulsion system, that's a discrete flag. So we have a mix of continuous and discrete design variables. And that then becomes the realm of the genetic algorithm. And so what we've done is we've used the non-dominated sorting genetic algorithm 2, or NSGA2, in order to optimize these vehicles for us. And we've optimized it with respect to multiple objectives. So it's multi-objective optimization. And those objectives could be maximum takeoff mass, the energy used per unit distance per unit payload, which is basically, think of it as a kind of an energy efficiency metric for the aircraft. Energy mass fraction, so how much of the overall mass of the aircraft is battery or fuel mass, and then mission time, how long are you taking to complete the mission. So we let the genetic algorithm do a bunch of different optimization setups. So these are listed in this table, and all of them are covered in great detail in our recent SciTech paper, but we'll focus on just a few of them. All right, so now let's focus on a two-objective optimization where mission time, so the time needed to complete the mission, and of course maximum takeoff mass. These have been specified as the two objectives, and we're basically saying, all right, now optimize based on these two objectives and for an 80-kilometer trip distance, and tell us what you get. And here we see the Pareto front of the final generation. And we find that for this short trip distance, the optimizer has basically eliminated the hybrid and turboelectric architectures and gone only with all electric. So at short trip distances, all electric is going to end up being lighter than hybrid or turbo. And here you see the Pareto front, which is basically telling us that this is the best we can do. If we want to go any faster and complete the mission in less time, our maximum takeoff mass is going to increase pretty significantly. Why? Because the propulsion system is going to have to be sized up. Its mass is going to increase. That's going to increase the mass of the whole vehicle, which is going to further increase the masses of the motors and the props of the lifting system. And so there's going to be a chain reaction, which is going to result in a very substantial mass penalty, a 600 kilogram maximum takeoff mass penalty for a 3-minute time savings. So basically what this is telling us is that there's very little to be gained by trying to go significantly faster. All right, so now let's look at a slightly more complicated optimization scenario where we've taken two different battery technology levels and we've taken a longer trip distance, 120 kilometers. And very interestingly, the Pareto fronts over here show all three architectures, which is significant because what we're getting from that is that the optimized final generation is not down to one propulsion system architecture, but it's basically cohabited by all three propulsion system architectures. And they have different advantages and disadvantages. So if you look at the energy efficiency, which is energy consumed per unit payload per unit distance, the all-electric scores better in that department simply because the efficiency of the battery to thrust power path is a lot higher than the efficiency of the fuel through the turbo generator system to thrust power path. So the all-electric is more energy efficient. However, as a result of battery technology state of the art, it's also significantly heavier than the hybrid and turbo electric architectures. Those are not as energy efficient if you think about it in terms of joules required to move unit payload, unit distance. However, they have significantly lower mass. Similar observations, but more pronounced, were observed for optimization scenarios where the trip distance was increased even further. So 150 kilometers, it basically just amplified these results. The all-electric architecture quickly became very, very heavy in terms of takeoff mass. The hybrid and the turbo-electric architecture not as heavy. Okay, and then I mentioned that geometry plays a central role in our activities. So here are some snapshots of all-electric, hybrid electric, and turbo-electric vehicle designs that came out of PEACE. So we depicted by a wireframe geometry, but it's actually a very detailed definition of where all the propulsors are located, how big, what the outer mold lines of the fuselage and the lifting surfaces are, and so on. So the observation that you see over here, basically reflecting what we saw in the graphs, in the charts, is that the hybrid electric, once the trip distance is above a certain threshold, the hybrid electric ends up being the lightest and the most compact vehicle design of the three propulsion architectures that we considered. Okay, now to wrap up, what are some conclusions and observations? Well, we have the PEACE framework that enables us to do sizing and performance analyses of a wide range of flight vehicles, novel configurations, and propulsion system architectures. So, so this is a powerful capability that we use a lot in our lab to further our research. And some important features with respect to the analysis of eVTOLs. We explicitly considered control allocation and trim, and we explicitly considered post-failure and off-nominal scenarios for power sizing. This is absolutely crucial because, as we saw, those trim and post-failure scenarios directly sized some of the power system components. So if we do not analyze trim, if we do not analyze post-failure scenarios, we will end up under-predicting the power and weight associated with the propulsion system. Further, that these vehicles that got sized using PEACE directly feed into our MADCAST framework. So in our second webcast, we will see how that MADCAST framework is used for control law development. In the third webcast, we'll see how it's used in our simulators as part of piloted simulation studies. And so all of it starts from that pipeline, from sizing, using PEACE. So we're trying to establish this workflow for novel concepts and propulsion architectures. Work still to be done, obviously improving the fidelity of our underlying analyses, replacing some empirical weight estimations with physics-based weight estimations for components, and also more detailed propulsion system component models. So these are areas that we're working on actively. All right, I think I'm right at the 45-minute point. So that concludes my formal presentation. So thank you, everybody, for your attention, and be happy to take any questions.
Yeah, Iman, it looks like we have our first question was from Santino Bianco. Santino, do you want to ask it?
I'm sure. And So I guess is there a published paper available that presents these sizing results? And then
Yes.
I've added a paragraph explaining some of the work that I've done in the past.
Okay. Somehow I'm not seeing this paragraph. Heather, should I be able to see what Santi wrote?
Yeah, his chat says that he has a dynamic model of the NASA revolutionary vertical lift technology, lift plus cruise powertrain. It's a skeleton model that has not been populated with realistic sizing information. And so I think your topics today were new information for him, and he's interested in populating the model and performing studies that assess the design during transients, such as the transition from vertical to horizontal.
Okay, perfect. So even though I tried, I could not see that comment. But Santino, what I would say is my email's on this, on these slides. So I would love to get in touch with you and see what kind of joint studies we can do. Now, regarding papers, yes, there are a bunch of them listed over here. So there are a bunch of papers that you have links to over here on slide number 12. So the PDF is being uploaded. And then the most recent work on this pipeline is the 3 papers we presented most recently at SciTech are here. So they're back-to-back presentations, and these hyperlinks should still exist in the PDF.
Great, thank you.
We have another question in the chat from Christopher Silva at Ames. Christopher, do you want to ask your question?
Yeah, so I had looked at the papers and you had the graphics in here too. You chose an interesting arrangement of the rotor rotation and the cant angles. Yes. And so when you put in a yaw input, and yeah, there you go. That may be the better graphic there, because the coloring there, as I understand it, is the rotor rotation direction. So counterclockwise in green, clockwise in red.
Right.
And so when you put in a net, or when you put in a pure yaw input, typically you would increase the rotations all in one direction and then reduce the rotations going in the other direction, the rotational rates going in the other direction. Right. When you do that for this aircraft, you end up with a net roll input as well. So is there any particular reason why you chose a configuration that would do that?
Yes, so let's go to another. This one will show the direction and the cant angle.
Right, yeah, that's the one I was thinking of.
So the idea over here is, if you look at each rotor individually, the cant angle and the rotation directions were chosen such that the torque that would be generated by increasing thrust on that rotor, just the torque about the axis that's generated, the aerodynamic torque, the direction of that yawing moment and the direction of the yawing moment generated as a result of the cant are going to enforce one another. Okay?
Correct.
So and so when we did some quick calculations, we found that the torque about the axis is not insignificant. So we really didn't want those two to be fighting one another. So now in order to increase, I wish I had the control allocation matrix over here. It will definitely be there in next week's webcast. It is entirely possible that there will be a rolling moment, but our lateral directional control allocation and the controllers that we developed for that, those consider roll and yaw control simultaneously. So when we've done simulations with this vehicle, if we put in a pure yaw input, there really isn't too much of an off-axis roll response, even if there wasn't a closed-loop roll control active.
Yeah, that's interesting. I mean, just by inspection here, the center of lift moves such that you will get a roll moment.
Right.
But maybe it doesn't move enough to be noticed. Maybe it's something that you only pick up with a motion simulator, and the fixed base simulator doesn't give the pilot or the passenger that sensation. Thank you.
Iman, we have a question online from Dan Murray, our former flight mechanics technical fellow and a pilot. Dan, would you like to ask your question?
Sure. Hi, Heather.
Hi.
So my question is, how do you account for thrust-induced aerodynamics? So you talked about using strip theory for lifting surfaces and a blade element momentum theory for the propellers. But what about the thrust-induced aerodynamics? They're going to be huge on a configuration like this.
Right. So it comes down to how much we've been able to capture versus how much we haven't yet captured. So we've captured the effect of the slipstreams of each of these props on the booms that are underneath them. Okay, so we've captured that in terms of a like a blockage effect, a reduction in their effect. What we have not captured within the APPM that we have so far is suppose in forward flight, like one rotor influencing the flow that goes into the other. So rotor-rotor interaction is at the moment not captured within our APPM.
Okay, and I had another question. It looks like your current method assures trim, at the flight condition you're evaluating. Does it also ensure adequate stability and control margin for maneuverability, such as through transition or upsets due to gusts, or is that future work?
So for let me answer that question in two parts. So for forward flight mode, what I didn't have time to mention in this is when we're doing our stabilizer sizing within piece, because we have we're able to solve for trim. The immediate next step we do after that is to perturb it along each state so that we get a linearized model whose eigenvalues we can compute. And that's happening within the sizing framework. So now we know what the dynamic modes are, and we can see whether they're stable or unstable. So our tail sizing procedure for this configuration is to pick the smallest tail that will guarantee mil standard, I think 87, 85 dynamic stability criteria on the short period and control anticipation parameter to be satisfied. Now for vertical flight mode, there will be some unstable modes. For instance, hover or low speed forward flight. We are not, as part of the sizing process, we're not directly accounting for maneuvering margins. We are doing it when we're optimizing the flight control system and the control laws, which will be the topic of next week's webcast. So we are looking at some ADS 33 rate and attitude requirements for level 1, and that is part of the tuning of the flight control system. But so far, we haven't found that the power requirements in order to achieve that so far have not exceeded the power that these motors got sized to based on the failure criteria that we already enforced, which is single prop failures or battery pack failures, high hot hovering conditions.
Okay, I'm looking forward to your future webcasts. I think the maintaining adequate stability control for these highly propulsion dominated configurations going through transition, that's the real challenge for this class of vehicle, I think. So this is really interesting work, and I'm looking forward to your future webcasts. Thank you.
Thank you.
Did anybody online want to ask a question? You can raise your hand or put something in the chat. Okay, Iman, I had a question for you. You talked about how important it was to consider failures in the sizing, your power failures. Does this also include like underperformance, not necessarily a complete failure, but propulsive and I apologize, I'm a spacecraft person, not an aircraft person, but how significant is it for underperformance from rotor to rotor system in the sizing? Is that accounted for in the dispersion space?
You mean one of them making partial power instead of completely failing?
Yes.
Yeah. So the case of complete failure ends up being kind of the more extreme case. So if you're able to deal with that, then you would also be able to deal with a partial power scenario on one of the props. Now, the caveat there is, okay, is it partial power, constant partial power, or is it out of control pulsating power? So that now becomes more of a question for when we start doing the time domain simulations with this thing. So that would be something we would test in our simulation models, which we'll cover in the next week So we could take one of the rotors and then put them through an out of control pulsating power profile and see how the rest of the flight control system is now going to react to that out of control rotor. But for sizing, we try to consider the more extreme scenarios where something's failed completely, contributing nothing, except a lot of moment imbalance. Yeah.
Okay. And yes, we have just a few more minutes. Let me get to Nan Nguyen out of Ames. I hope I said that right. Your question?
Yeah. Hey, Iman, how are you?
Hey, how are you?
Good. Hey, I have a quick question. Maybe I'm missing it, but did you account for the structural effects like the elasticity? I can notice that you have your wing loading.
Yes.
I mean, your proposal way out the wingtip, and and the potential for this kind of like flexibility that could interact with your proposal thrusts.
Right.
I just don't know how you account for that.
Yeah, so we that's one of our works in progress. So we're working on something for the aviation conference in June, where what we're trying to do is we're trying to replace the wing weight estimation we've got now with more of a physics-based one that actually considers what you said, which is how far out span-wise the torque and lifting loads from these booms will be. So that would go one step towards that. As for complete air elasticity, we haven't gone, because we're doing conceptual level sizing. We haven't created like a NASTRAN model and tried to see what kind of structural modes would come out, and then figured out a way of factoring in that effect into the conceptual design stage. So in the form of a weight penalty. So this is at the moment unexplored territory for us.
Yeah, great. Thank you.
Okay, well, let's thank you, Iman, for sharing this topic with us today, and we're really excited about the two upcoming webinars. Please be sure, if you do have any follow-up questions, to reach out to him. I think his email is in the charts, and it's also on the recording. If you need to reach out to me or Alex Walker, we can help make that connection for you. We look forward to seeing you guys at the next webinar, and thank you again, Dr. Chakraborty, for this great topic.
All right, thank you, Heather. Thank you, everybody.